We flip a switch, we plug in our phones, and we just expect power to be there. We think of it as this steady, reliable river of energy. But behind that wall outlet, there's a secret world, a world of pulsing waves, invisible forces, and some seriously brilliant engineering. Today, we're going to pull back the curtain on the secret life of AC power.
So let's start with a simple question. You get that electric bill every month, right? But what are you actually paying for? Seems obvious. You use electricity, you pay the bill. But what if I told you that a chunk of the power being sent to your home, or more likely to a factory down the road, isn't actually doing any useful work at all? To figure that out, we have to dig a little deeper into what power really is.
So, here's our game plan. First, we're going to shatter the myth of steady power. Then we'll meet its two very different personalities. After that, we'll tackle the big problem of efficiency, and then we'll uncover the incredibly clever solutions that literally power our entire world. Ready? Let's go.
Okay, first things first. That idea of a constant, smooth flow of electricity coming through the wires, well, it's kind of an illusion, at least when we're talking about the typical circuits in our homes.
Take a look at this graph. This is what the power in a standard AC circuit actually looks like from moment to moment. It's not a nice flat line. It's this wave that's constantly pulsing up and down. And you see where it dips below the zero line? Yeah, that means for a split second in every single cycle, power is actually flowing backwards, away from the device and back toward the power plant. Wild, right?
This pulsing, constantly changing value has a name: instantaneous power. It's the real, moment-by-moment truth of what's happening in the circuit. And understanding that power isn't steady, but choppy, is the key to, well, everything else we're about to get into.
So, if power is always pulsing around like this, how do we even make sense of it? Well, engineers came up with a great way to think about it. They split it into two different jobs or two different personalities. Let's call them the worker and the field builder. First, you've got real power. Think of this as the worker. This is the good stuff. This is the power that actually does something useful. It makes your toaster hot, it lights up the bulb, it spins the motor in your blender. It's the part you actually want and use. But then you have this other thing, reactive power. This is the field builder. This power doesn't do any work itself. Its entire job is to build up and then collapse the magnetic fields that things like motors and transformers need just to operate. It's absolutely necessary for them to run, but it doesn't contribute to the final task. It's all setup, no action. And to see how these two fit together, engineers use this really handy visual called the power triangle. The bottom of the triangle is our real power, the worker. The vertical side is the reactive power, the field builder. And that diagonal line, the hypotenuse, that's called apparent power, and it represents the total power the utility has to generate and send down the line just to deliver the other two. And now you can probably see the problem, right? The power company has to supply that entire diagonal line of power, even though the only part that does any real work for you is the bottom edge of the triangle. This whole situation creates a big efficiency problem. We measure this efficiency with something called the power factor. It's just a ratio of the useful power to the total power. A perfect score is 1. That would mean the triangle is totally flat. All the power being sent is doing useful work. But if you have a lot of that reactive field builder power, the triangle gets tall, your power factor drops, and the utility has to work way harder just to get you the same amount of useful energy. And believe me, this isn't just some abstract concept. It's a huge deal in the real world. That wasted effort still heats up the power lines and forces the utility to build bigger transformers and generators. It costs everyone money. That's why power companies get really serious about making sure big factories have a power factor as close to perfect as possible.
So what's the fix? You can't just eliminate reactive power because all those big motors need it. Well, this is where engineers get really, really clever.
So check out these two triangles. On the left, you've got your inefficient system. The motor is creating a lot of reactive power, making that triangle tall. But here's the magic trick. It turns out that another component, a capacitor, creates the opposite kind of reactive power. So if you add the right size capacitor to the system, as you see on the right, the two reactive powers basically cancel each other out. The triangle shrinks, and the whole system suddenly becomes way more efficient.
And the impact is, well, it's huge. In this example from the source material, just by adding a capacitor to improve the power factor from a pretty bad 0.6 up to 0.8, the amount of current they had to draw from the grid dropped from 10 amps down to 7.5. That's a 25% reduction. They're getting the exact same amount of real work done, but with so much less strain on the system.
Correcting the power factor is an awesome fix for a single piece of equipment. But for powering the entire grid for the whole system, engineers came up with an even more beautiful and elegant solution.
Remember this guy, our old friend, the pulsing power curve from the beginning? That up and down, choppy delivery of energy just isn't great for big, heavy-duty motors, and it's not the best for sending power over long distances either.
And now for the big reveal. This is the magic of three-phase power. Instead of having just one AC wave, the power company generates 3 of them, all perfectly spaced out. And what happens when you put them all together is just incredible. As one wave is dipping down, another is rising up to take its place. The end result? The total power being delivered is a perfectly smooth, constant flat line. No pulses, no dips, just a beautiful, steady stream of energy.
Okay, I know. That's a lot of triangles and waves. But why does any of this stuff really matter? How does this invisible dance of forces actually impact our daily lives?
Well, it matters because that smooth, constant three-phase power is the secret sauce that lets us send electricity efficiently across the country. It's what gives massive industrial motors the steady, powerful torque they need to run our factories. Managing power factors saves an incredible amount of energy, which means lower costs. All of this, it's literally the invisible backbone holding up our entire modern world.
So, the next time you flick on a light switch, maybe you'll think for a second about what's really happening. It's not just a simple flow. It's an invisible dance of 3 waves, perfectly timed, working together to keep that light steady and bright. It's a pretty amazing reminder that even in the most ordinary things, there's usually some extraordinary science at work.